All right, I'm going to do some of the problems from 7.2. So these are all solids of revolution or solids with cross-sectional areas given, those kind of problems. And we'll start with number 11. They said to find the volume of the solid that's generated by revolving the region that is bounded by y equals the square root of x, y equals 0, and x equals 3. So first let's start off by doing a sketch. I think it's a good idea to actually sketch it with points, like real points, so that you kind of can see bounds easier. So I know that 0, 0 is going to be a point, 1, 1 is a point. If I plug in 4, it gives me 2, and that is probably enough. So there's my function. But it has to be bounded by y equals the square root of x, and also bounded by x equals 3, so that line right there. And the area that we're talking about is this one. So we're going to be taking this area and revolving it around the x-axis. Let's figure out what the radius is. So the radius is always starting from the axis of revolution, because that's like the center, to starting from there to the outside of whatever the curve is or whatever we're talking about. So when I revolve this around, it's going to be kind of like this, kind of like a bowl or a cone that's not very pointy. The radius is that, and notice that the radius changes when I move it left and right. So the radius needs to be an expression that changes. In this case, because it's up and down, an up and down distance, it's a y distance, and our y is defined by the square root of x. So that means my radius is square root of x. So this one's not too hard, because it's just going to be pi r squared. So 0, or pi from 0 to 3, because we're bounded at x equals 3. So pi r squared, so it's going to be square root of x squared dx, which will pi, so that'll be pi from 0 to 3. Sorry, square root of x squared is just x. And so if I actually do that integral, I'm going to get pi times x squared over 2 from 0 to 3. So I'm going to get pi, and I'm just going to leave the pi on the outside. So I'm going to have 3 squared over 2 minus 0 squared over 2. So really this ends up being 9 over 2 pi. And I actually did not bring the solutions manual home with me, nor did I bring a calculator, so I'm not checking my work. Hopefully I'm not making too many careless mistakes. I think that the rest of the problems are actually a little more interesting. I actually really like the one where it has to go around the y-axis, because there's a lot of thinking that goes into this one. So let's think about if I go around the y-axis. If I look up here at my drawing, I'm no longer rotating around the x-axis, but instead I'm going to be rotating around the y-axis, so I'm going to kind of clear a little bit of this off. That means that I'm going to be rotating this way around the y-axis. So notice that when I kind of do this shape on the other side and try to imagine this three-dimensional shape, there is kind of a gap in the middle, like it's kind of a funnel-shaped gap. And so this is going to end up having to be the washer method, because it's not just one big solid. There's a piece missing out of the middle. So I mentioned before, you always need to start with the axis of revolution. So if I start with the y-axis and go out, that distance right there is 3. And it's actually 3 no matter where I go. If I move that line up or down, notice it's always 3. So I'm calling 3 my big R. That's the outside radius. So imagine this shape is kind of like a solid cylinder, but then it has this funnel cut out of it. So the funnel part is a little bit more interesting. The distance from the y-axis to the curve. Notice that it does change, so when I move that line up and down, it gets smaller and bigger, so I know that needs to be some kind of algebraic expression. Because it is horizontal, I know that it needs to be like an x equals situation. And so that's where we have to take our original equation and change it into an x equals. So if I solve this for x, it's going to be x equals y squared. That's our little r. So our little r equals y squared, because that is that x distance as I move up and down. The other thing that's kind of different is when you're graphing with, or sorry, when you're rotating about the y-axis, or really any vertical line, you need to have everything in terms of y. So I kind of like to make a note. It's more of a mental note, but I'll go ahead and write it down. If I'm rotating about the y-axis, then that means I'm going to have a dy. That means my equation is in terms of y. And I need to have y bounds. So that's the only thing we haven't talked about yet. If I look back up to my graph, it starts at 0, but how do we figure out where it ends? I know on the x-axis that it stops at 3 because of the bounds. So if we think about the original equation, y equals the square root of x, I know that it stops at 3 when x is 3, and so actually my top bound on the y-axis is square root of 3. That's what that point will be. So just recap real quick. Big R is 3, little r is y squared. So I'm going to do the integral from 0 to square root of 3. And remember, I'm going to do pi. It's essentially like pi big R squared minus pi little r squared. I'm going to go ahead and factor a pi out to the front. So there's big R squared, and there's little r squared. You make sure it's not r minus r squared, but r squared minus r squared, dy. So simplify a little bit. 9 minus y to the 4th, dy. And if I take that integral, I'm going to have pi times 9y minus y to the 5th over 5. And I'm going to evaluate that from 0 to square root of 3. And that's not going to be very pretty. That's okay. You can have things with with roots in them. That's totally fine. I'm going to go ahead and skip to part D because part C and part D are similar, and part D is a little bit trickier. So still the same equation, the same bounds, and this time the axis of revolution is x equals 6. So I'm going to draw a white dotted line where the axis of revolution is. Okay, so again, imagine, and I'm actually going to erase this little extra piece of the square root of x function just so we can focus on the area. If I rotate this around here, the first thing I notice is this gap right here. That's going to end up being little r. Because if I try my best, again, this is very much just a sketch, but if I try my best to kind of reflect the shape over and try to imagine this spinning around, looks kind of like a dome with a cylinder cut out of it, I guess. So you can see pretty easily, I think, that little r is just 3, because from 3 to 6 is 3 units. So that is 3. The one that's harder to see is what the outside radius is, what big R is. So if I go from here to here, or here to here, here to here, notice that that is big R. It's always bigger, but it's still changing. So it needs to be some kind of expression. Then if I check right here, keep in mind, we already found that the distance from the y-axis to the curve was y squared. So that means the yellow distance, the distance from 6 over to y squared, would be 6 minus y squared. So big R is 6 minus y squared, little r is 3. My integral is going to be in terms of y, so it's going to be from 0 to square root of 3 for the same reasons as above. And then it's going to be r squared minus little r squared dy. On the AP exam, You will not necessarily have to do this by hand, but if you do have to or have a calculator, you would still need to write this integral expression down the way that I have it written down. But then you can type it in your calculator and be like equals, and then just like say what it equals instead of actually doing all of the work to show how you took the integral. But if it's non-calculator, obviously you would have to actually work it out. Okay, pi. I cannot actually do this yet until I simplify this expression right here that I just underlined in yellow, because I can't do u substitution because then I would have a y in there and I don't have that. So if I do the good old pattern of square, square, multiply, double, that will work, or I can distribute that all the way out. Okay, so I'm here. I can actually subtract the 9, so I get 27 minus 12y squared plus y to the 4th dy. And if I take the integral of that, the pi will stay in the front, but then I'll have 27y minus, it'll end up being 4 because it's like y cubed over 3, and then it'll be 12 divided by 3. Plus 1/5 y to the 5th, and you would need to evaluate this from 0 to square root of 3. All right, number 29. I went ahead and graphed this in Desmos and copied and pasted it so it would be a little bit neater. But they wanted you to find the area between these two curves, and then it needed to be between 0 and 3, so that's kind of interesting. First off, it might be helpful to see where these two functions intersect. So I set them equal to each other. I started solving. I need to factor out a 2, and that will make this easier. And when I factor this, I end up getting x minus 2, x plus 1. So I know that they hit each other at x equals negative 1 and x equals 2. The x equals negative 1 doesn't matter a whole lot. The x equals 2 is helpful. So since we're doing the area between the two curves, from 0 to 3, because it said the bounds were x equals 0 and x equals 3. There's kind of two different areas here. There's this pink area that has the red curve on top. And then there's going to be this green area which has the blue on top because I'm going from 0 to 3. So this is actually going to be two separate integrals because you know how we normally do top function minus bottom function, or like big R minus little r. And the problem is that the big R and the little r change since they kind of switch. So this one was an interesting question. Okay, from 0 to 2, I'm going to look from 0 to 2. So remember, this one, it actually stated your axis of revolution was the x-axis. So if I start on the x-axis and go out, my big R is the red function, which was the negative x squared plus 2x plus 5 function. So that's my big R. And then my little r is the blue function, and that is x squared plus 1. So my first integral is going to be pi 0 to 2 of r squared, big R squared minus little r squared. Definitely going to guess that this would be a calculator question. So that's going to give you the volume from 0 to 2, like of that pink one if I revolved it around the x-axis. But then I'm going to need to add to that the integral from 2 to 3. And if we look from 2 to 3, this time, I'll do it in blue. The axis of revolution is still the x-axis, so I'm going to start there. If I go out to the outermost function, see now that it's x squared plus 1. So that's my big R. And if I go from the x-axis to the other function, that's the little r. So So little r is the negative x squared plus 2x plus 5 function. So that integral is going to be pi times 2, the integral from 2 to 3 of big R squared minus little r squared. Zeke woke up from his nap, hence the TV in the background. dx. And I would anticipate that to be a calculator problem. You probably would enter that whole thing in. For number 72, I'm not going to do the whole thing because it asks you to do 4 different versions of this problem with different cross sections. And actually, this is like almost exactly the same example that I did in class. It's nope, it's not y equals. It's x squared plus y squared equals 4, and that is the equation of a circle with a radius of 2. So it kind of looks like this. Part B asks for equilateral triangles. So I know I've said this a few times, but I'm going to just keep saying it for emphasis. All of these problems were essentially adding up all the areas of the cross sections and then multiplying it by the change, kind of the height of what that little tiny 3D cross section would be. And so that's like the area of the cross section times dx or dy, depending on if you're perpendicular to the x-axis or perpendicular to the y-axis. This particular one said perpendicular to the x-axis, so I know it's going to be a dx problem. With an equilateral triangle, I know the area of an equilateral triangle is square root of 3 over 4 times the base squared, or the side squared. So the thing that I need to really figure out, so I know I'm going to be doing the integral from negative 2 to 2 of square root of 3 over 4 base squared dx. So I need to figure out what that base is. So I'll look back over at my picture. I'm going perpendicular to the x-axis. I'm going to draw a line perpendicular to the x-axis. So imagine, it's a little hard to visualize it, but imagine all these red lines are the base of an equilateral triangle, and the equilateral triangle is like coming out towards you, so it's pointy in the middle. I need to figure out what that base is. So notice it changes. And just like we did when we found area, it was like the integral of the top function minus the integral of the bottom function. That was because the distance between those was the top minus the bottom. This is a circle. And we talked about this in class. But if I were to solve this equation for y, like I would subtract x squared, and then I would take the square root, and it would actually be plus or minus. The top function, which I'm going to do in green right now, is represented by the positive square root of 4 minus x squared. And the bottom function, which I'm doing in blue right now, is represented by the negative square root of 4 minus x squared. So the distance between those two, I'll do in yellow, is going to be positive the square root of 4 minus x squared minus the negative square root of 4 minus x squared. That's just top function minus bottom function. And this ends up, of course, turning into a plus, and there's 2 of them, so I get 2 the square root of 4 minus x squared. That actually equals my base. That's that distance. Okay, so let me plug that in. The integral from negative 2 to 2, square root of 3 over 4, which I could just put that on the outside if I wanted to. 2 square root 4 minus x squared squared. Technically, that is one whole term since the 2 and the square root are being multiplied. So I'm going to do square root of 3 over 4 on the outside, negative 2 to 2. If I square this, this is going to be 4 times 4 minus x squared dx, which of course is going to simplify to, and you know what, I might actually even go ahead and divide this 4 and that 4 and leave the square root on the outside. So here I am. square root of 3 times 4x minus x cubed over 3 from -2 to 2. And then I would plug that in and evaluate.